The universal law of gravitation. So basically, gravitational force is responsible for all the planets which are revolving around the sun, like Earth revolving around the sun, Moon revolving around the Earth. Let's understand what is this force, how it is working, and how all the planets are able to revolve around the sun. So we have talked about the free fall. So gravitational force keeps the moon and the earth in their orbit. Orbit is this path, as you can see, this white dashed line in which earth is revolving. So this is earth's orbit, this is moon's orbit. Its nature is attractive, like the force can be force of attraction or repulsion. So this is force of attraction. And all the bodies, when they fall towards the earth, again the gravitational force is there. So straight line motion for falling bodies and revolution in the case of celestial bodies, they are caused by gravitational force. So according to the Newton's third law, every action has an equal and opposite reaction. For example, if you slap somebody, if you slap very hard, your hand hurts, right? And the cheek of the person also hurt. Why? Because every action has, like, the forces are applied in the opposite direction. So a force causes large acceleration when applied to a smaller mass compared to that of larger mass. So now let's understand gravitational force. As you can see here in this picture, the earth is pulling this mango towards its center. This is because of gravitational force, and this is called gravity. So there is a law which is also called Newton's third law, that every action is combined by equal and opposite reaction. Like if there are two objects, if one is pulling, let's say there is a object A and B. If A is pulling B, B will also pull A. So there is action force and reaction force, and they are equal in magnitude, means equal in value, and they are opposite in direction. So what is the reaction force for the gravitational pull? Like if the mango is falling towards the ground, this is action, okay? What is its reaction? Why earth is not moving towards the mango? If according to Newton's third law, the earth should also, attract mango. If the, earth is attracting mango, so mango should attract the earth, right? If there is action and reaction force. If stone is falling, and from the building, it is dropping and earth is attracting it towards earth, why earth is not moving towards the stone? Where is this reaction force? Is the Newton's third law wrong? Let's see. So this is the third law. Every action is accompanied by an equal and opposite reaction. So what is the reaction force for the gravitational pull by the earth on different objects? So gravitational pull of the mango on earth, the mango also attracts the earth towards itself with an equal and opposite force. This is what third law means. But we can only see mango falling towards the earth. Why don't we see earth moving towards the mango? Or same here, right? So yeah, the question is here, why we do not see earth to be moving towards the mango or towards this ball? Basically, the answer is given by Newton's second law. For a given force, acceleration is inversely proportional to mass. If the mass is like less, the acceleration is more. Okay, so um, like they have inverse relation. Mass, more mass, less acceleration, less mass, more acceleration. This is what Newton's second law says. So basically, if you compare the mass of mango with mass of earth, the mango mass is very very less as compared to earth, isn't it? So that's why the acceleration of mango is much greater than the acceleration of earth, and that's why we can see the mango falling or accelerating towards the earth, not earth. Basically, the acceleration of motion of earth towards the mango is also there, but it is very very small for us to notice. That's why we do not see earth moving towards the mango. Okay, it because this acceleration means how velocity is changing, how speed is changing with time. This is opposite as like this is inversely proportional to mass. So the earth also moved towards the mango as a result of this gravitational pull of mango on earth. However, the acceleration of the earth towards the mango is very small, and that's why we ignore it and we cannot see. It is not, we cannot see. And the same goes here. Um, so why do we not see the earth to be moving towards the mango or the ball? Similarly, the mass of moon is very small as compared to that of earth. So because mass of moon is very small as compared to earth, so mass of I mean the acceleration is more because they are inversely related, right? So the earth also moved towards the moon as a result of this gravitational pull, but acceleration of earth is very small, that's why it is not apparent. um, so yeah, that's why we only see moon to revolving around the earth. So now, is there a similar force of attraction between other object? um, for example, here if there are two trees, one is applying a force on another, the another will also apply the force on this one, right? This is what gravitational force is. So the gravitational force is the force of attraction. It is not only between earth and other object, it exists between any two objects in this universe. So this is given this basically by Newton, Sir Isaac Newton, and he gave a law which is called the universal law of gravitation, that it exists between any two mass in the universe, which is a force of attraction. And the formula is this. This is what it says: every object in universe attract every other object with a force which is directly proportional to product of their masses and inversely to square of the distance between them. Here you have m1, m2, these two mass, there is a distance d, a is applying a force on b is applying a force on a, as you can see here. Now, this is the universal law which says that force is directly proportional on these two mass and inversely with this r distance. That means if we increase the distance, the force will decrease. If we increase the mass, the force of attraction will increase. Okay. So if there is a force of attraction existing between any two bodies in the universe, why do objects not move and stick to each other? Like if there is attraction, they should, just attract so much each other. They should just like if there is a force of attraction between the sun and the earth, why don't they collide? Why don't they stick together, right? And yeah, so here is a question. If we there are two masses, one is 55, other is 64, and the distance between them is 2 meters, what is the gravitational force between them? So why like this question answer we will understand here, okay? You can see two people, their masses and their distance is 2 meter, right? So as I said that gravitational force is between any two object, any two mass. If these two people are sitting next to each other, there is a gravitational force between them. Then why don't they stick together? Let's calculate the gravitational force between these two people, okay? This is the formula. The value of G is this. Mass m1 is given 55, m2 is 64, and the distance is 2 meters, so 2 square, which is 4. So if we plug the values, we get this. Do you see this is 10 raised to power negative 8? Negative 8 means if I divide it with 1 and put 8 zeros in the denominator. So negative 8 means it is very, very small. Okay. So the force of attraction is there, still there, but it is very small. It is negligible. This is why we do not seem, to experience it or to stick two masses together. Okay. Now, yeah, yes, we can. Just 1 minute. Now, importance of universal law of gravitation is why it is called universal, because it is applicable to any two bodies in this universe, no matter how small they are or how large the bodies are. It is applicable everywhere in the universe. So basically, it explains many natural phenomena. For example, the force that binds everything on Earth is this: the motion of moon around Earth, all the planets moving around the sun. All these are explained by the universal law of gravitation. The high and low tides due to moon and sun. So that's why it is very very important. Okay. So we learned about the gravitational pull, its formula, why it is called universal, what is its